Hello, students. So, if V happens to be a vector space and it's finite dimensional, we are finally ready for the following definition. Let V be a finite dimensional vector space. So we know it's spanned by finitely many vectors. We also know that it has a basis made from finitely many vectors, because if it's spanned from finitely many vectors, we could always start taking vectors away to form a basis. We've already proven that. Vector space. The dimension of V, written as dim V, is the number of vectors in a given basis. Okay, we know that any basis has the same number of vectors, so this is a well-defined definition. What about infinite dimensional vector spaces? Let's maybe not talk about those right now, but you might want to think. You might just want to say, hey, what would the ways be in which we could extend this definition in the infinite case? So that's something you might want to consider. But that's not where we're going. We're sticking to finite dimension. We have a bunch of things left to show. So, for example, what we could show is if U is a subspace of V and the dimension of V happens to be n, that's sloppy, and the dimension of V happens to be n, then the dimension of U has to be less than or equal to n. And this is easy to show, because proof, well, any basis for U consists of independent vectors. And you know what, let's say, I'll call that M. Let's say there are M independent vectors for some value M. But what do I know? I know these independent vectors are sitting inside V, and V is spanned by n vectors, so therefore by that same theorem about sizes, since these are in V, and V is the span of n vectors, we have M less than or equal to n. So, that's our proof. That's what we wanted to show. And we are done. So, first proof, now that we have our new definition about dimension. So subspaces always have a dimension that's smaller, or I should say less than or equal to the dimension of the original space. The next result is maybe a little more surprising. That's a little obvious. I mean, we're taking a subspace, you think smaller, okay, smaller, so you'd expect maybe the number to be lower. But here is a very important result. Let the dimension of V be n. Any n independent vectors is a basis for V. So what does it mean for the dimension of V to be n? It means that we have n vectors which span V, and those n vectors are independent. So we have some collection, one collection we're thinking about, of n vectors. They're independent, they span V. Okay. What this is saying is any collection of independent vectors that we pick, as long as they're independent and they're the same number, they will form a basis. Okay? Well, there's actually a number of ways to do this. One way is to start with fewer vectors. So for example, proof, well, to try to start with fewer vectors, we can't. Suppose v1, v2 through vm is, oh, I should say vn, is a collection of vectors in V which are independent. So we have these vectors, they're independent, they're inside V. We can extend them to a basis. If they're not a basis, we could extend them. Because we have a result about that, where we can always add vectors to form a basis. So if they are not a basis, we can extend to v1, v2 through vn, and u1, u2 through uk. Okay? But if k is bigger than 0, what do we have here? We have more than n vectors that are independent, because it's a basis, so they're independent, in a vector space of dimension n. And we know that any independent vectors must be less than n. So therefore, I should say, k must be 0, meaning there are no u's, or we would have a basis of different length. And what does that mean? Well, if k is 0, that means this was a basis to begin with. So any collection of n vectors inside a vector space of dimension n, if you have n vectors and they're independent, they form a basis. Okay, so we can see that this idea, this definition of dimension is already important. We're able to state some important things in a nice, concise way using it. Two things so far: that the dimension of a subspace is always less than or equal to the dimension of the space, and also that if we have the same number of vectors, it equals the dimension of the space, then if those vectors are independent, they form a basis, whatever they are. So this allows us some nice ways that we might be able to construct a basis, because as long as we can ensure independence, we're good. It'll make it easier for us to find bases in the future, but I think I'm going to end this here.